So, that was a nice presentation of yours. I will give a relatively theoretical follow-up of something I presented last year, namely, what are photons? And photons these are the things that we use all the time, and it puzzles me that there is this energy or this wave particle duality. And last year we tried to dive in a little bit deeper, and now I add the capability of models to predict the value of photon shot noise. And photon shot noise is something we know very well. Everybody was either theoretically or you measure it. We know that when you have an integrating sensor, that the noise in ideal situations, if you exclude all artifacts, precisely follows the relation that the standard deviation of the signal is square root of the signal itself. And these are two expressions that make this. And we know that this expression is right because we measure it all the time. And in many cases, we have a second way to check this reality. You can, for example, by this method, you know what is the full well, but you can also measure the full well in an indirect way by knowing, for example, the capacitance precisely. This is a figure that you all know, but I want to show it to Kennedy. Because the signal is exactly the square of the noise, if you would measure the noise in the red curve and you measure also the signal in the green curve in a unit that doesn't matter, it can be AC units, volts, whatever. If you see that there is a factor 10 between them at a certain point, it means, and there is no other solution, that if there is a factor 10, it means that you have 100 electrons, of which 10 noise electrons are emitted. This allows the y-axis to be calibrated. You can, for example, know what is actually the separation charge, what is the noise charge, what is the CVF, etc. And now let's go to the photon models. Last time we just said there are a lot of models. What is a photon? What is this quantum? And what you learn at secondary school is something like a photon is a bullet. Why? Photon is a bullet. But you could say this is intuitive, but it doesn't explain anything. It doesn't explain interference. We could say a photon is actually a short wavelength, which allows explaining certain things like polarization, but not interference. You could assume that these bullets are actually very large wavelengths, larger than the experiment, so that it could explain interference effects or dual slit effects, but not at the same time, unfortunately. So to be sure, bullet models explain quantization because these are quanta. It explains intuitively, but not with formulas, conservation of energy, and it explains, for example, the experiment electron-positron annihilation creating two gamma rays can be explained by that, at least can be made interpretable. What is, however, difficult to explain is that at the site of the emission, at the site of the light source, photons, according to quantum mechanics, should have a Poisson distribution of emission, and at the detecting end, it should also have a Poisson distribution of emission. And if you are not careful, you have 2 times photon shot noise. But we will see that this is not really true. Bullet models cannot explain interference. They cannot explain 2 slit experiments where particles go via one split and another split and then they combine. Even small wavelet models cannot explain that because the wavelets are so small that they will not go through 2 splits at the same time. You must already go to large wavelets, which as the word wavelet is maybe wrong, where the whole experiment is included in the wavelet. But then you cannot explain other things. What is this electron-positron annihilation? It is a well-known process. I actually experienced it myself this process is used in PET scans. This is a medical equipment where you try to see where in the body is a certain cancer located. What happens is electrons are everywhere available in material. Positrons have a very short lifetime, but when a positron meets an electron, they annihilate. And in that process, two gamma rays or gamma photons, if you want to name it like that, will emerge in almost opposite directions, precise opposite directions, and they will also happen at exactly the same time. This seems to be an explanation or a justification of a bullet model. This acts like a bullet. It's precisely in that direction, simultaneously. There is no randomness, or at least the seeming randomness is not random because they happen at the same time. Modeling that as plain Maxwellian electromagnetic waves is awkward. Now, there is the bullet model and there are the Planck models. Planck, the scientist Planck, originally proposed quanta as the amount of energy that a charged particle gives or takes from an electromagnetic wave. It is an amount of energy, and it is not a bullet, it's an amount of energy. And this is the original idea of Planck. The light source gives a quantum of energy to the wave, and the wave is an energy wave. An electromagnetic wave is energy. And then at the photodiode side, it gives back an amount of energy to the photodiode. It is possible to, there is something I can already tell, this does not obey Photon Shot Noise, because there are two independent processes at the beginning and end, and whatever you try to do, the Photon Shot Noise of such a process is larger than what we measure. So you could make it match by saying, well, the electromagnetic, let me rephrase a little bit, because there is randomness in the amount of energy deposited in the energy wave is noisy. Because the energy wave is noisy, that photon shot noise comes on top of the already noisy energy wave. It's like a noisy light source creates extra noise apart from the photon shot noise. You could say we dictate that the energy wave is not noisy, it is noise-free. Then there is indeed, there will be no discussion what happens at the receiver end, but there is discussion what happens at the emission end. Having energy deposited from the light source into the wave makes, strictly speaking, no sense. It will happen, but it is then actually more a probability that is dictated by the DC level of the probability that a Poisson distribution or a Poisson probability of having a quantum of energy put in the wave happens. It's a little bit fishy. It is difficult to interpret, but such an electromagnetic wave is rather a probability distribution, which reminds of the quantum mechanical wave function. The quantum mechanical wave function can also be interpreted as a probability function that is called the Born interpretation. So let's review the Planck one, where the intermediate electromagnetic wave is noisy, is not DC. It can explain in great detail interference. Interference is completely explained by that wave. Double split experiments, polarization are explained. Planck 2 is a variant where we say the wave is noise-free. And if the wave is noise-free, the emission process and the absorption process are independent processes, and we have a problem with synchronicity. Because this famous experiment, electron-positron annihilation, it is very clear that there is a correlation between the emission and the absorption. You could say the absorber diode randomly absorbs a neutron, nice, but we know it's not random because another diode also absorbs a neutron at exactly the same time. So Planck 2 cannot be true if we believe that the PUT scanners work. And they also don't explain entanglement. Entanglement is something that must be used to explain Planck's 1 or the bullet models going through polarization classes. So we came then to transaction models. Also, and a transaction model means the following. Bullet models don't work. Planck models don't work. Is there something that works and that can explain everything? And that is maybe that the process of emission and the process of absorption of a quantum are linked. They happen together. They happen always in pairs. It poses a few difficulties in our view of the world. Why would, for example, an emission photon be paired with an absorption photon at some distance, at some other time, whereas there are many other possibilities? So there must be something like a probability that this transaction happens and the others do not happen. An electron can interact with any other electron in the universe on the condition
Computer says no.
and I go back. So a transaction model, what can you do with it? What is the value? It's not just a fancy idea. It's useful because it can explain things. It can explain the value of photon shot noise. The photon shot noise is exactly what we measure because the process of emission and absorption is together a Poisson process. You don't need hidden variables. There are no such thing as hidden variables to explain, for example, polarization experiments. It can explain entanglement. Actually, it doesn't need it. It can be considered as an expansion of Planck 2. In Planck 2, the electromagnetic wave is a probability. And now we can say, well, this probability covers emission and absorption, whatever is in between, and it's also a probability. Because Planck 2 can explain interference experiments, we silently assume that such a probability distribution would also explain interference experiments. What are now the drawbacks? A transaction model contradicts whatever we intuitively think of reality. For example, if you would have a photon that arrives here and started at the beginning of the universe, at the Big Bang, it means that it already agreed with the absorption happening here, that this would happen with a time span of 15 billion years in between. So the causality, distance, elapsed time, the arrow of time are completely not intuitive. Let's now look to these photon models, the same using photon shot noise. The bullet model at point of emission. So at this place, the variance is equal to the expected value. That are the abbreviations. The variance is actually standard deviation square. You don't doubt, this is a Poisson process. But at the end, it is a little bit different. The expected value, how is it? If you would have a photodiode with 100% quantum efficiency and you offer it 100 photons, it will give you 100 electrons without noise. Of course, these 100 electrons have been created before with photon shot noise. So it will end up in the right way. Suppose you have a photodiode with 50% quantum efficiency, it will convert the 100 on average incoming photons to on average 50 electrons. So that is high. That distribution is a binomial distribution. Just for your information, I write here the equation for binomial distribution, where n is the number of photons that impinge, p is the probability for conversion, which is dus the quantum efficiency, and the quantum efficiency also applies to this. The incoming electrons, the incoming photons are E1, the resulting photons from them are dus V1 multiplied by quantum efficiency square. And for this particular case, the V2 is 0. I calculate, you can calculate, and I will not bother you with that because it is not really the essence of the message. That if you calculate the total variance, you find out that the total variance still obeys Poisson distribution. And the nice thing about shot noise with a bullet model is that the shot noise is not purely due to the emission, it is not purely due to the absorption, but there are cases that it is pure emission or that it is pure absorption. That is funny. It is as if the diode, the light source, and the photodiode make a deal. Say, how much photon shot noise do you have? Oh, I have that value. Oh, that's not the real value. I will add something so that it becomes the real value. But of course, it is just a mathematical thing. Planck models and photon shot noise. At the absorption side, a photodiode will absorb from an electromagnetic wave precisely photon shot noise, meaning the variance is equal to the expected value. At the emitter, the Poisson process will result in the precise square root photon shot noise equal variance equal to emitter. If there would be no attenuation, if all photons really will go until the photodiode, which you could realize by making a shiny metal tube with a LED and with a photodiode, you could theoretically do that. You would have a variance that is double the expected value from photon shot noise. We know that it is not true. For all practical cases, B and E are okay. You cannot, in theory, in reality, you cannot really make a light source for which all the photons really end up in the photodiode. In reality, you lose the light goes other ways and the emission is not perfect. So in all practical cases, the effective variance is the theoretical variance divided by A, in which A is an attenuation factor. Also, the effective amount of photons that come out of a light source will be the maximum number of photons that come out of the light source divided by attenuation. And if you calculate the total variance of the full process, the total variance will be the variance due to the absorption plus a finite value. This is not the photon shot noise formula, it is larger. Maybe it is a little bit larger, but it may vary. So it contradicts photon shot noise. That's why we came with Planck 2. If you impose that there is no noise in the electromagnetic wave, the electromagnetic wave does not contain information of the photon shot noise of the light source. And we will thus have pure photon shot noise at the end. That means for Planck 2 is the best model. Unfortunately, the electromagnetic wave is thus DC, does not carry temporal variation, and phenomena like electron-positron annihilation don't fit that model. Transaction models, if we say the photon emission, transmission, and absorption are one transaction, actually that is proposed by Kramer in 86. We must conclude that this is the only process that can explain everything. bullet models cannot explain diffraction experiments, but Planck models can. But Planck 2 cannot explain two photon observations, and Planck 1 fails the photon shot noise magnitude. Actually, what I think is there something else that is not transaction, and it's not Planck, and it's not bullet? In transaction models, the emission and absorption are linked, and they have a common origin. The absorption of a photon and the emission of a photon are linked. It's one process. It is difficult to grasp. And when I previously mentioned that, who remarked they are not so far away. For a particle or something traveling at light speed, it is a bit as if time stands still. So there is no time elapsed for a photon, and there is no distance traveled for the photon. So from the standpoint of the electromagnetic wave or from the photon, emission and absorption are almost at the same time, at the same place. They are at the same place and at the same time. So from an outside, from an external observer, an electron or charge loses impulse and energy. That information or that energy travels, and there is an elapsed time and distance. And another charge Q gains that h times. That's for an external observer, but for the thing itself, it's just as if it is touching the other charge. That's difficult to grasp, but it is not so far-fetched, because that's what general relativity teaches us. If you travel at the speed of light, there is no distance, there is no time. And then the electromagnetic wave is a probability. The transaction model suggests that electromagnetic waves are a probability distribution and are not energy being transferred, or they do that, but yeah, how can you swallow that? How can you, because this changes our worldview. I always thought that electromagnetic waves carry electromagnetic energy, but you could say it is a probability distribution. And in fact, the wave function, the Schrödinger equation, is also interpreted as a probability function. This is one of the interpretations. That is the interpretation that became famous by the cat of Schrödinger. And by the way, the wave function or the Schrödinger equation reminds very strongly to the Maxwell equations. It is a kind of Maxwell equation with different parameters, but it has a similar look and feel. Another equivalence which may make this digestible is that the energy transmission through an electrical wire. You think that energy through an electrical wire is carried by the electrons traveling through that electrical wire. It is not true. The energy goes in a mantle over the wire, outside the wire. Difficult to understand. It is like that. Or at least the Maxwell equations teach us that it is like that. Or it is like the electron is not just a very small round particle. The electron is actually the Coulomb field outside the electron, which goes very far, and multiple nanometer. Actually, it goes to infinity decaying. If we now want to see how each of these models explains reality, but I mean, should really take reality. Photon shot noise is for me very real. All of you measured once or more times photon shot noise. It works. The electron positron experiments, this works. I experienced it myself. Two split experiments. You have probably done that in a high school. You have probably done the two split experiments with high flux, but if you do the two split experiment with low flux, that means a light source shines light, it goes through two splits and you have one absorber. If you do that in a situation where the light flux is so low that on average there is no photon or just 0.01 photons at the same time in the experiment, still there is interference. How can that be explained? The only way to explain two slit experiments is either 0.2, because the wave interferes and we don't care about what started, but also the transaction model can explain that. So for me, essentially, photon shot noise, the electron-positron annihilation, and the two split experiments, there is no model that explains everything at the same time, except the transaction model. And maybe I'm taking my wish for granted. As we are talking about that, entanglement, hidden variables, spooky action on a distance. Can we say something? This is again the transaction. An amount of the quantum of energy for a photon gives or takes impulse from particle, for a charged particle, and then some time afterwards and at some distance, another particle gains that energy or gains that impulse. That is the transaction. But from the standpoint of the wave, this happens at the same time, like two billiard balls hitting each other. So entanglement is the absorption photon is entangled to the corresponding emission photon. And entanglement, I don't really know what it means, but it probably means it has the same quantum numbers, it has the same impulse, it has opposite directions, it is happening simultaneously, it has the same spin, it has the same polarization, it has the same frequency. That's entanglement. So entanglement from that standpoint is, well, the absorption is entangled with the emission. Actually, it is not even the photon, it is the electron or the charge is entangled with the charge involved in the emission. If you would now have two particle interactions, like the electron-positron emission, this electron will create a photon, which is a gamma photon, which will eventually hit a charge in a photodiode. And now we assume that this electron is entangled with this original electron or with this original photon. And the other pair, the positron, will also create a, well, it is not that the positron creates a gamma ray and the electron creates a gamma ray. It is more sophisticated than that, but this is, let's say, a simplistic view, and I don't know how this could be made more sophisticated. But there is entanglement of this gamma ray to the absorbing gamma photon acting on this charge. Now, the absorbing photon A is entangled to this emission photon B. Why is that? Yeah, because it's a transaction. This emission photon B is entangled to the emission photon C because this process is a purely symmetric process, electron-positron, and you can accept this is symmetric. So B is entangled to C because they happen on the same place at the same time. C is entangled to D because this is a transaction. The causality is B and C are entangled because they were really locally happening at the same time. And B is entangled to A because of transaction, and C to D because of the name transaction. So D is entangled to A. D is entangled to A, and the hidden variable is actually C and B. And there is no spooky action on a distance. So entanglement, as entanglement is explained as two or more particles, which in our case is photons, we don't know anything else. They have entangled quantum numbers, including position, impulse, polarization, whatever. These properties they have, that is because they are entangled with their creation moment. For photons, this is the emission of the photon, being part of the transaction. So if two or more photons are emitted in a common process, they have identical or symmetrical quantum numbers, etc. And also if particles are added later to the bunch, for example, in quantum scattering, some form of entanglement is remaining. Now, qubits and qubit computers. I had someone arguing about qubit computers and he was extremely enthusiastic. He couldn't explain me what was a qubit, and I tried to reverse engineer what is a qubit. What is a qubit? It is different from a bit. A bit is something that is 0 or 1, and a qubit is something which is a wave function. That means probably a probability, which is an amount of 0, an amount of 1, and you don't know how much. And the qubits that are being made have kind of pockets to put an electron in, and these electrons have entangled spins. Spin is something like a rotation direction of an electron, and if you know the one spin, you know also the other spin, even if you manage to position them far apart. But now I think these electrons have obtained that spin at some creation event, or at some event in which they were imposed a spin. Probably that means they were close together. So measuring the spin of the one implies knowing the spin of the other. Oh no, you know the spin at the creation event. So it is not the cat of Schrödinger. The cat of Schrödinger says the cats are alive or dead at the same time. No, now it would be the cat is already dead, and its death has been created some time ago. And the hidden variables that are claimed to exist for the cat of Schrödinger are actually the quantum states that are manifested at the creation event. And then I read very interesting things about qubits. A qubit-based computer can calculate all possible superpositions at the same time, but I don't think it is true. It will simply calculate that single case to which it is entangled from its creation event. And I thought, if qubits would really be useful, what should be their property? And maybe I'm missing something. Maybe entanglement or hidden variables is something else than what I think. If I would make a computer based on data storage, like bits, but a superposition of everything that is possible, I would start with making transfer information infinitely fast. And what qubit people claim is that you have an electron with a certain spin here and an electron with a certain spin here. I measure the spin, bloop, I know the spin here. This is information transferred faster than light. Now, honestly speaking, that is stupid, because I could have sent encrypted data in both directions, and I will desencrypt the data, and I know immediately what happens there, and you will desencrypt it. I don't think it's like that. It looks like with a bedrag when you transfer. What I would really find convincing is I have a cube with spin. I have two electrons with a spin, and here the opposite spin. I bring them apart. I don't know the spin. And now I change the spin. I would be able to change the spin to up. Let's change it up. And if that one would instantaneously change to down, then we would really have infinite speed of data transmission.
Very fast in a inverter.
This is probably not possible because there is just one reason why it might simply not work. I think it will simply not work, but a convincing reason why it might not work. Suppose I measure this guy before I change that guy. Will he then, in retrospect, still change? That's like the cat of Schrödinger. The cat of Schrödinger has a spin. I measure here the spin of the cat of Schrödinger. I see, that's. And I go and look. The cat is dead. But suppose I first go and look to the cat. Cat is still alive. Then I change the spin here. The cat is dead. No, I don't believe this. So I think QBITs are a fraud. Where a particle is entangled to multiple other particles, it is by entropy not possible to determine the entanglement. That means two particles are entangled just purely to each other. But if there are other things like scattering or interference, then it becomes a mix and you cannot know that. And people making qubits do a lot of effort cooling the thing. They cool the qubits because otherwise they have a finite lifetime. What probably happens is that there is scattering so that this full entanglement simply dilutes. Okay, the arrow of time. It is a kind of claim in nature that most elementary processes are symmetric in time. And the photoelectric effect and the laws of Maxwell are symmetric in time. The equations are just symmetric in time. You could reverse the motion picture. The things that are flagrantly not symmetric in time are the increase of entropy. If I would, for example, have all the air molecules at one side of the room, they would normally fill up the room. The opposite will not happen. But there are written transactions. Things are a little bit different. And this is something you know. Suppose at the emission, that means at the light source, a photoelectric effect creates a quantum with an energy equal or less than the available energy step. You know that the band gap, the photon that you can create by emission, is less energy than the band gap. At the absorption, it is equal to or more than that. You need a bigger, or you need a higher energy photon to create an electron hole pair in a photodiode. You cannot reverse that. You cannot let the LED give current because you put current in a silicon photodiode. It works only in one direction. You can say, yeah, but microscopically it is still symmetric. That is true. Also, the two photons, when you go to electron positrons making two gammas, that happens spontaneously. You just leave a positron and go to an electron and poof, you have that. You must do not do anything special. The inverse does not happen, or it has never been observed. You cannot just shine two gammas together, and then expect that an electron-positron pair comes out. That doesn't happen. Similar things happen, but not that. Then
like the first one you can do with gamma rays, and the WISPO interaction.
Yeah, but that is not electron-positron creation.
No, but the first one.
Yeah, but there is always a delta.
There is a delta.
It is not exact.
But it happens.
You cannot do the Mossbauer in the other direction. It's asking. Entanglement is slowly lost by weak scattering. It means entanglement is actually an entropy increase. And as we know, if you want to counteract entropy increase, it costs you energy. Cleaning a room costs energy. Letting it become dirt goes automatically. Creating full entanglement, and if you read the papers about creating entanglement, you see that these are power-hungry processes. And then transactions, a transaction if you put, and I cannot, if you put describe a transaction as something like Maxwell plus something quantum mechanical, these formulas are just time symmetric. But the fact that we add this relativistic observation that you have zero distance and zero time, that works only in one direction. So arrow of time may not be symmetric. So I have conclusions. Perhaps, I always say perhaps, a photon is actually a transaction of impulse and energy described like that. Two charge carriers exchange impulse and energy, and they are separated in time and space, but from their own standpoint, they are just touching. What happens in between for an external observer is a very wide probability field, which may be the electromagnetic field, but from their own standpoint, this is the probability that happens in one point. Perhaps, or a transaction model for photons can explain all phenomena of electromagnetic interaction, and that is nice. And due to conservation of misery, we have to pay a price, like in Faust, the devil asks something in return, and what the devil asks in return is that we abandon our perception of time, causality, distance, etc. Why is the transaction model remaining? Because actually the two main alternatives, bullet models or electromagnetic field or Planck models, fail to explain all observations. But yes, maybe there are others. Maybe there is something else than bullet models, Planck models, or transactions. There are some consequences. The elapsed time of a transaction from the point of view of the electromagnetic wave is zero. From the photon standpoint itself, it happens at the same position in space and time. So entanglement, meaning having correlated quantum numbers, is just intuitively obvious. Second, perhaps space and time, as we see that, is a projection. Perhaps distance and also distance in space and distance in time is an asymmetric concept. We have intuitively the feeling that the distance from here to here is the same as the distance from here to here, and we learn that in mathematics, but maybe it's just not true. It's a perception. We see that, but it is not that. The hidden variable of photon absorption is the corresponding emission photon. And electrons, if the distance between an electron and a far away electron is just zero, an electron simply touches or sees all other electrons in the universe, at least those that are at x equal to t times light speed of light distance, meaning wherever you can go at speed of light, those charges are actually touching you. And only those are possible transactions. And there are apparently more conditions. You must also have a matching both that H Planck constant times frequency. Why is that? Because nature tries to play riddles with us. The emission absorption pair must have the same frequency. Otherwise, all electrons would simply interact with all other electrons and it would be a mess. And maybe nature has made some order. Maybe because these formulas, for example, the Schrödinger equation contains this I, which means square root of -1, and also the laws of Maxwell contains the square root of -1. If you write it in a certain way, you as electronic engineers, you know what means square root of -1. For us, I or J means at a certain frequency. That's it. For us, it's logical that I means at a certain frequency. So all these formulas are at a certain frequency. Maybe this is the obvious explanation why interactions from one photon to another, even at a long distance, are at the same frequency. Okay. Any questions or remarks, or maybe Bert, you crazy also.
My brain is a little bit fried. I need time to process it. Did the Planck model come from Planck himself, or is it just something they call it now?
He did experiments with black body radiation, and he couldn't understand the experiment unless he had to accept, but it was not willingly. He said it is a mathematical artifact, but it looks like energy from a charge carrier to an electromagnetic field goes by quanta. That is a quantum. He was not convinced about it. Stuff like that.